Hello, this is another lesson on exponentials and logs, so pure chapter 14.5. There have been 4 lessons before this one, this is the 5th one. Today we're going to be exploring the relationship between exponents and logarithms, what the main link between the two is. So first of all, as ever, there's going to be a warm-up of 4 questions, here they are. So if you could copy these out, try them first, and then only play the video when you've tried your own solutions, you'll get the most benefit from doing that, rather than just copying down my answers. So have a go at these first, then proceed when you've done them. So, right, let's have a look together at the solutions to these, see if we can make sense of them. So the first one, question 1, we have 2 cars, P and Q, that are moving on a straight horizontal road with constant velocities. The velocity of P is 15i plus 20j, so this is a vector question, and the velocity of Q is 20i minus 5j. Find the direction of motion of Q, giving your answer as a bearing to the nearest degree. So it's a bearing question as well as a vector question. So what we need to do is think about what this motion of Q means. So the motion of Q has this direction here. And so the unit vector I is going to the right, the unit vector j goes up. So if it's minus 5j, that's going down. So this is meaning it's 20 to the right and 5 units down. So if we imagine as a vector, we always start from north, of course. So let's draw the north line in first of all, like so. Label that N for north. So for every 20 across, we go 5 down. And so the direction of the motion is going to be something like this, just going slightly downwards. So it's going to be below the horizontal. So it's going to be below this line here, obviously. So obviously we know this is going to be 90 degrees, this corner here. This is the motion of Q, and so what we're needing to find here is this angle. And what I'd suggest we do is to do 90 degrees plus this one here, which I'm going to call theta. And using what we know about the direction of Q, it's 20 along and 5 down, and so the magnitude of this line would be 20, and we can call this one 5. And so this is actually now just dropped into being a fairly simple trig question. And so the total bearing is going to be this 90 degrees plus theta, which we can work out using trig. So the bearing, cutting to the chase, is going to be 90 degrees plus tan minus 1, because you know the opposite and the adjacent, so tan minus 1, 5 over 20. So we can work this out pretty easily, to be honest. So we get the calculator up. So 90 plus shift tan minus 1, 5 over 20, or just 5 divided by 20, which I'm doing here. So we get 104 degrees. To the nearest degree, which is the same as 3 sig figs in this case. Next one, question 2. So again, using what we had from question 1, at time t equals 0, the position vector of P is 400i meters, and the position vector of Q is 800j meters. After time t, the position vectors of P and Q are P and Q respectively. So first of all, we need to find an expression for P in terms of t. Okay, so what's going to be happening here is P is going to be starting off at 400i. But for every 1 second that goes along, P is moving along. P is actually moving a bit. So in terms of what we have for P, if we just toggle back to question 1, P is moving along 15i units plus 20j. So every 1 second that goes on, it's going to go 15 along and 20 up. So in terms of t, after t seconds, it'd be a multiple of t in that direction. So it's going to be 400i for starting, plus t lots of 15i plus 20j. In other words, this is the starting position vector. This is the speed. It moves this much every 1 second. So we take this here and multiply it by how many seconds it's moving in this direction for, basically how much time it's moving in this direction. Very similar for Q. So Q is starting off being at 800J relative to some fixed origin. And then its speed, just going back to question 1 for a moment, its speed was 20I minus 5J. So after t seconds, we're going to have this. And part B, we're asked to find the position vector of Q when Q is due west of P. So the big clue for this question is if Q is due west of P, then they're on the same horizontal line. And so they're in line horizontally. So if Q is due west of P, what the implication of that is that the J components of both P and Q are equal. So now we can go and work this out. So in terms of the J components, because J means how far up or down, because they're horizontally the same, the J is going to be the same for both. So for P, the J component of P is going to be 20t. So t times 20, that's 20t. And for Q, the J component is going to be 800 minus 5t. So 20t equals 800 minus 5t. So simply rearrange this. So 25t equals 800. So therefore we know that Q is going to be due west of P. After 32 seconds, after 800 divided by 25. So that's got us nearly to where we need to be. So what we do now is we can substitute in that the t value, the time, must be 32 seconds. So let's pop that in for Q. So the position of Q that's going to be 800J plus 32 lots of 20I minus 5J. And so if we just substitute this in, so 32 times 20I is going to be 640I. And the J component, 800J minus 32 times 5, that is also going to be 640. And so that is the position vector of Q. Question 3, we have a fairground game involving trying to hit a moving target with a gunshot. So a round consists of up to 3 shots. It's not saying it's necessarily 3 shots, but it could be up to 3. So 0, 1, 2, or 3. 10 points are scored if a player hits the target, but the round is over when the player misses. So Linda has a constant probability of 0.6 of hitting the target, and shots are independent of one another. Essentially, this is going to be a binomial distribution idea. So part A, find the probability that Linda scores 30 points in a round. So if she scores 30 points, just think about how she could do that. If it's 10 points for a hit, and she's got up to 3 shots, that means she's got to hit the target with every single shot. So the probability of getting 30 points is the same as probability of all 3 hit the target. So the probability of hitting target once is 0.6. So hitting it twice would be 0.6 squared. Hitting it 3 times in a row would be 0.6 to the power 3. And so that's going to be 0.6 0.216. For b, we need to find the complete probability distribution of x. And so what we need to do here is to draw up a table. So I'll just do one here quickly. Oops. So with this table, we need to be thinking about the probabilities of getting 0 hits, 1 hit, 2, 3, 4, and 5. And how that can be done each time. So x could be anywhere from 0 to 3. No hits, 1 hit, 2 hit, or 3 hits. So now we need to think about the probability that our random variable takes on each of these particular values. So we've worked out from part A that she has 3 hits. Oh, apologies, it's the number of points Linda scores in a round. So not a number of hits, but a number of points. So if it's 10 points for each hit, we can just multiply these by 10. So the chance she got 30 points, we've done that one already. That was 0.216. So think about how she could get 0 points. Well, she gets 0 points if she missed straight away. So that one here is if she missed. So we're told this essentially. The chance of her hitting is 0.6. Therefore, the chance of her missing would be 0.4 for any one shot. So the probability that she misses straight away and stops is 0.4. Next up, we need to think about the chance of her getting 10 points. So to get 10 points means she must hit once and then miss. And so that's a probability of hit then miss. So probability of her hitting the target is 0.6 and then missing, so times by 0.4, 0.6 times 0.4 gives us 0.24. Whereas if she gets 20 points, that can only be done if she hits twice then misses. So that's the probability of hitting once to get 10 points, hit again to get another 10 points to give her a total of 20, and she misses, so she stops on 20 points. So 0.6 for a hit, times 0.6 for another hit, and then times 0.4 for a miss. So if you tried that on a calculator, 0.6 times 0.6 times 0.4, that gives you 0.144. As a double check, what you could do is sum all these probabilities, and they should get to 1. If you check this now, you should find that they do. So just to show you here that they do sum to the right value. So 0.4 plus 0.24 plus 0.144 plus 0.216, 1, which is what you'd expect. Finally, for the warm-up, question 4, Calculus Corner, we need to work out this indefinite integral. And so what I'd suggest we do first of all is to write this down in index form. And so we've got 1 plus 3x to the half. The square root is the same as power half. And then 1 over x squared is the same as x to the power minus 2. And so this is what we need to integrate. So we'll integrate a constant. That 1 is going to become 1x, which is just x. Thinking of being a definite integral there, sorry. So the 1 becomes an x. Here, the 1 increases, so this 1/2 increases to a 1, and so 1/2 plus 1 is 3 over 2. So the x here becomes 3 over 2, and we divide through by that new power. So 3 divided by 3 over 2 becomes 2. And then the new power becomes 3 over 2. And over here, x to the power minus 2, we add 1 to the power, So that becomes a minus 1, and we divide through by the new power. So this minus 1 divided by minus 1, we get plus 1x to the minus 1. And one thing we need to remember when we do a indefinite integral is we need to remember the constant of integration. So we need to add on this c. And that's all the warm-up questions done. Okay, a bit of work for you to do again, even after the warm-up. So this is just to get your head around and to consolidate the ideas from the previous lesson or two about how logs work. So in each row, you need to circle the odd one out. So after you've circled the odd one out, you then need to write a logarithm in the fourth and final column of equivalent value to the ones you've not circled. Okay, so the idea behind this is I want you to remember how the log of a number relates to the base. So have a go at this yourselves, then press play when you're ready for me to explain and show you some possible answers. Okay, so the log of a number, for example, log base 2 of 32, just to recap from the other time, the log of 32 is a power to which we need to raise the base to get this number 32. So the answer to this one is what power of 2 do we need to get 32? So for this one, that would be 5, because 2 to the power 5 gives us 32. So these two here are the same, whereas log base 2 of 16 would be 4, because 2 to the power 4 gives us 16. And so we need to circle this one as the odd one out. Next, we need to think of a log, which is the same value as 5. So I'm just going to go for log base 10. And so 10 to the power 5 would be 10, well, a 1 with 5 zeros after. So 1, and 1, 2, 3, 4, 5. Because 10 to the power 5 would give us this number. And so that's one possible answer out of infinitely many. Row B, 10 squared would be 100, and so the answer to this one is 2. 7 squared would be 49, and so this one is also 2. Whereas this one here would actually be a half, because you need to raise 9 to the power of half to get 3. The square root of 9, in other words, is 3. So this one, the odd one out, is this one. So now what you need to do in the final column is to write a log where the answer is 2. And so, I don't know, I'm going to go for log base 2. So 2 squared. Well, 2 squared is 4. So the answer to this one would be 2, because 2 to the power 2 gives us this number. Row C, slightly harder, but not so bad. So this one here, log base 2 of 8 would be 3, because 2 cubed gives us 8. But 8 cubed, that would be 8 times 8 times 8. And so this one would be 3 times 3 times 3, which would be 9. Again, if you're not sure, check it with a calculator. But this one here, you need to raise 2 to the power 3 to get the first 8, then multiply that by another 3 to get the second 8, and another 3 for the third 8. So it would actually be 3 plus 3 plus 3, sorry, which would be 9. This one here, log base 2 of 4 is 2. But 2 to the power 4, sorry, 4 to the power 4, would obviously be much bigger. And so we need to do that 2 4 times. And so 2 times 4, that one would actually be 8. And so these two aren't the same. Whereas here, 2 to the power 9, that tells us that we need to raise 2 to this power 9 to get 2 to the power 9, obviously. And so this one is 9, and that one was 9. So the odd one out is actually this one here. And the idea here is to think about how the power relates to the log. Log base 2 of 2 is just 1, whereas log base 2 of 2 to the power 9 is 9. So it's almost like we can bring this power to the front and multiply it by log base 2 of 2. We're going to mention that later on. So anyway, these two here are equal to 9. So what we could do here is make another log. I'm going to go for log base 3 this time, which is, I'm going to say 27. 3 cubed is 27, and so if I do 27 to the power 3, that'll be 3 plus 3 plus 3. 3 times 3, which gives us 9, which is the same as the first and the third column, which is what we want. Finally, row D, log base 2 of a half, that's 2 to the power minus 1. So this one is equal to minus 1. Log base 4 of a quarter, that again is 4 to the power minus 1, because it's a reciprocal of 4. Here though, log base 4 of 1 over 16, that's 4 to the power minus 2, that's 1 over 4 squared. And so the other one out here is this one, because that equals minus 2. So one we could do here, I'm going to go for log base 10 again, of the reciprocal of the base. That would equal minus 1 again. Now what I'd like to do with you is to derive the laws of logarithms step by step, so we can then use them and apply them in different questions. So we're going to start with statement 1. Consider the two exponentials, a to the power m, which we can call x, and a to the power n, which we can call y. So now we need to write each statement as a logarithm. Okay, so going back to previous lesson, this is base a, so write log base a of x, that must be m, and likewise over here, log base a of y, that must equal n. Now, what I normally do is to just relate it to a log I remember. I can only really remember like a few logs. One I remember well is base 10. So log base 10 of 1,000, just for example, is the power of 10 we need to raise 10 to get 1,000, which is obviously 3. And how does that relate to a power? Well, 10 cubed is 1,000. And so this is just a nice link to help remind you of how logs relate to exponentials. So I'm just going to put this in the corner, should you get confused or unsure with the more abstract algebra. Anyway, step 3. Using the law of multiplication of indices, find the product x times y as a single power of a. Well, xy is this thing here, which is a to the power m, multiplied by y, which is a to the power n. And obviously you know now that when we multiply indices together with the same base, we add the powers. And this is the same as a to the power of m plus n. Step 4, we can write this as a logarithm. So from before, if a to the power m was x and a to the power n was y, and we can think of this in terms of log of xy. So if we just think about this here, we've got x to the power y is a to the power m plus n. So let's just write this first of all. And think about how the power of the base links to the answer. So here, for example, 3 and 1,000, we put the 1,000 next to the log, and the power as the answer, if you like. So therefore, what we can say is this base we put under the log, so log base a, and this time we put 1,000 next to the log, and that's going to be equal to the power that we raised the base to. So log base a of xy is going to be the same as m plus n. But for step 5, we can remember what m and n were from step 2. M was log base a of x, and n was log base a of y. So log base a xy is the same as log base a of x plus log base a of y. And that's the first important result we've got. Now let's see if we can derive the division law of logs. So step 6, we need to write x over y as a single power of a. So first of all, x over y, that's going to be a to the power m, which is x, divided by a to the power n, which is y. And we should know by now that when we divide indices with the same base, powers of the same base, we just simply subtract powers. And so this is going to be the same as a to the power of m minus n. And step 7, we now need to write this as a logarithm. And so first of all, if I just write down from step 6, we now have a to the power m minus n equals x over y. I'm going to link this back now to step 1 from above. And so the power, I'm just going to highlight in this yellow. And what this is, I'm going to highlight in green. And so obviously we don't have m, we have a different power. Instead of having it as x, we have a different expression. We've got x over y. But look now how this switches round when I rewrite it in terms of logs. We can put the answer in green, if you like, here. And we can put the power which we had at the end. And so using the same idea as we have for step 1, we can rewrite this. So we put log base a of, for green, which we now have as x over y, equals the old power, which was m, but now we've put here, it's m minus n. So using the exact same idea, but just now we have different expressions, that's all. Now we're nearly there. Step 8, we need to rewrite this in terms of logs. So we need to put m minus n in logarithmic form. And so now this is our final step. So log base a of x over y is the same as m, but m is log base a of x. Subtract n, which is log base a of y, and we're done. So maybe you see these are quite similar to indices, which should make no surprise to us because they're inextricably linked, indices and logs. When we divide powers of indices, we subtract the powers. When we're dividing expressions in terms of logs, we subtract each expression in terms of logs. So x over y is log ax minus log a of y. Now we need to do the power law. And so we're going to do this, first of all, by considering x equals a to the power m. So find x to the power k as a single power of a. So x to the power k, well, x is a to the power m. So that's going to be a to the power m itself to the power k. Remember, with indices, when we do power of a power, we multiply the powers. So that's going to be a to the power of km. We now need to write this statement as a logarithm. So if we do this here, and we can write down a to the km equals x to the power k. And again, I'm going to link this in to what we had from before. And so here, if I just put down the power of a in yellow, and the answer to that in green, and now rewrite this in terms of logs. And so log base a, now we put down the green expression first, so we're going to put down x to the power k. And now we're going to put in the yellow thing. Oops, not that, not green, but yellow. Then put this after. So log base a to the x to the power k equals km. So just linking it into what we had before from step 1, trying to use the same ideas to help us through in the understanding. So now we need to rewrite m. What m actually was, it was log base a of x, which we can see here. So we're going to rewrite this in terms of step 10. So then, now we have log base a x to the power k equals k multiplied by m, but remember m is log base a of x, and now we've done it. So that's the power law of logs. So let's summarize these results. So we've got the following important results. So step by step, the first one we arrived at is a multiplication law. Log base a of xy is log base a x plus log base a of y. The division law, log base a of x over y is log base a of x minus log base a of y. And the power law, log base a of x to the power k is k multiplied by log base a of x. So let's just think about a few special cases before we move on. So log base a of 1. And so this is going to be 0. I'll explain why. Remember, the log of any number is a power to which we raise the base to get this number. And so a to the power 0, in fact anything to the power 0, gives us 1. And so, therefore, we need to raise the base to 0 to get 1. B, log base a of 1 over x. There's a few ways I can derive this, but I'm going to use step A to help us. And the division law. So from the division law from before, that's going to be the same as, in fact, I'll write this on a different line. Log base a of 1 over x, that's the same as log base a of 1 minus log base a of x. Now log base a of 1 is 0, which we had before, minus log base a of x, which is obviously just minus log base a of x. Now we could have derived this as well by rewriting this as log base a of x to the power minus 1, and then using the power law of indices and bringing the power to the front of a log. But that's one way we could do it here. And finally C, log base a of a is always going to be 1. What power of a do we need to raise it to get itself? That's 1. A to the power 1 is a. And so we need to remember these special cases as well as the laws we've just arrived at in the previous steps. But let's now have a go at some worked examples using these ideas. So first of all, write as a single log, log base 3 of 6 plus log base 3 of 5. So what we should know here now is that this is the same as log base 3 of 6 times 5, using the multiplication law of logs. That's the same as log base 3 of 30. 6 times 5 is 30. For B, log, just double check it's the same base. Now we've got one log take away another. This is using now the division law. So this is the same as log base 7 of 20 divided by 4, which is 5. Part C, we've now got 2 log 5 to the 4 minus 3 log to the 5 of 2. You need to remember the power law. The same as log base 5 of 4 squared. That 2 we can rewrite here. In the same way here, we can write this 3 next to the 2 as a power. So that's minus log base 5 of 2 to the power 3. So what is 4 squared? 4 squared is 16. And minus log base 5 of 2 to the power 3, which is 8. Now I've got one log minus the other, and it's the same base. So now we can write this as 1 divided by the other, which obviously we now know that's log of 2. And now part D, log base 6 of 16 plus 3 lots of log base 6 of a half. Now what we need to do is rewrite this in terms of a power. So log base 6 of 16, and we write this as a power, so log base 6, put that 3 as a power of a half, so that's 1/2 cubed. Now we can work out what a half cubed is. A half times a half times a half is 1/8. So that's the same as log base 6 of 1/8. We can combine these into one log using the multiplication law of logs. So that's going to be log base 6 of 16 times 1/8, which is obviously going to be 2, and then we're done. Questions 2. So now we need to write these in terms of log of x, log of y, and log of z. So first of all, part A, rewrite this in terms of single logs. So first of all, what we need to do for this one is think about rewriting this using the multiplication law. So we can section this out into log base a of x squared plus log base a of y plus log base a of z cubed. But x squared isn't in terms of x, and z cubed isn't in terms of z. So we need to get rid of these powers, and if you remember the power law, we can bring the powers to the front of the logs, and it doesn't affect the value. So this is the same as 2 lots of log base a of x. Log base a of y, we can leave as it is, that's fine. And this one, we can bring the 3 to the front, and we get 3 log a of z. Part B, we can use the division law to do this as one log take away another. So log a of x minus log a of y cubed. So leave the log a of x on its own. This one here, we can bring the 3 to the front to give us 3 log a of y, and then we're done. That's absolutely fine. Part C, same idea as before. So this is a combination of the multiplication law. This top bit is a product, and the division law, because over z means we can divide all of this by z. And so this is log base a of x plus log base a of the square root of y, which is y to the power of a half, minus log z. So that's the same as log a of x plus half of log y minus log z. And finally now, part D, log base a of x over a to the power 4. That's the same as log base a of x minus log base a of a to the power 4. So we can leave log base a of x as it is. And this one here, we can bring the 4 to the front and say it's the same as 4 times log base a of a. But this special case here, log of a certain base of itself, that's the same as 1. So we can just leave this as 4. So then we have log base a of x, just subtract 4. Worked examples 3. So we need to solve these equations. So first of all, what I'm going to suggest we do is just remind ourselves of this fact. Well, I'm going to remind myself for my own benefit, if nobody else's. So I'm going to write down log base 10 of 1,000 equals 3, which is the same as saying 10 to the power 3 is 1,000. That always helps me to remember how they link into each other. Just put this there just as a reminder. So this one here, we can combine this into one log. So log base 10 of 4 plus log base 10, this 2 can be put here, of x squared equals 2. We can now combine this into one power, one log, so we have log base 10 of 4x squared equals 2. So now we can have a look and see how this links to this above. And so log base 10 of 1,000 equals 3, 10 cubed equals 1,000. So what we can see here, I'm hoping, is that 4x squared, I'll just colour code this in fact. So if I put 4x squared here, 4x squared, that's going to be the base multiplied by what was the 3, which is now the 2. So 10 cubed, 10 cubed, 10 squared, 10 squared. Just using this link here. So in other words, 4x squared equals 100. Divide through by 4, we get that x squared is 25. If we now square root both sides, we get that x equals plus or minus 5. However, just think about this. We've got x here in the log, okay? We can't take a log of a negative value, okay? We can't do that because we can only take logs of positive values. If you try it on a calculator, it would just simply blow up. So for example, log base 10 of say minus 2, doesn't like it, never will, never does. That's because if you take a number, for example 5, and do it to any power, the smallest you can get is 0. We can't go into negatives. So because of that, we need to get rid of the negative. And maybe put as a note, just to remind yourself, x can't equal negative 5. As we can only take logs of positive values. Only take logs of positive values. Part B. Solve this equation. So this here we combine into one log using the division law. That's the same as log base 3 of this over that. So x plus 11 all over x minus 5 equals 2. And again, from before, I'm just going to put up that other link. So I'm just going to skip back to question 2 for this link here, which I'm going to copy down because it's going to be useful. So let's just move this over, if I can. There we go. So we can now compare what this means. And so the log of what we're taking, in this case, x plus 11 over x minus 5, that must be the same as 3 squared, which obviously is 9. And so x plus 11 over x minus 5 equals 3 squared which is 9. Now we've got that link out of the way, it now becomes actually very simple. It just becomes a GCSE style equation to solve. So we can now multiply both sides by x minus 5. So now we get x plus 11 equals 9x minus 45. Get the x's to the same side. Get that 8x equals 56. Therefore, divide through by 8. That gives us that x must equal 7. And the final one of part 3, sorry, question 3, it's part C. Again, I'm going to use this link from before. Move it away. Come on, move, move, move. There we go. So let's get this into one single log first. So log base 2, 3 log base 2 of x, we can rewrite as log base 2 of x cubed minus log base 2. Square root of x, I'm going to write as x to the power half. And that equals 5. So this can be combined into one single log. So that's going to be log base 2 of x cubed divided by x to the half. But x cubed divided by x to the half, that's going to be the same as x to the power of 2.5, which is 5 over 2. So again, using this link here, so x to the power 5 over 2 is going to be the same as 2 to the power 5, which is 32. So x to the power 5 over 2, that's going to equal 32. So x is going to be, we can take this root of 32 to get the solution. So if we just put this here, shift root 5 over 2 of 32, we get that's 4. And so x must equal 4. So, now it's over to you to do these questions. So, page 323 and 324, exercise 14e. Try all the questions. Have a go. Leave me a comment if you get stuck, and do be in touch. So thanks for listening, and you'll see me again in the next video. Thanks for now.